Okay, this is going to be a very quick lecture for kids who were taking the MCA test in math. What we're learning today, this is for extra credit for your quiz tomorrow, so you can get up to 5 points extra credit. So I'm going to talk about VSEPR theory, and VSEPR theory stands for valence, shell, electron, pair, repulsion theory. And basically what this theory says is that you can predict the molecular geometry of molecules in chemistry by the fact that the outlying atoms align themselves around the central atom in such a way as to get as far apart from each other as possible because they're repulsed by each other. And so I'm just going to show you, go back to your 9th or 10th grade geometry and just show you how easy this is. So first molecule type is AB2. And AB2, I'm going to draw the picture. You got, what that means is you have A in the middle and you have B's on the outside. Well, if one B is here, one B is going to be here because they try to get as far away from each other as possible. Because the electrons, like if a good example of this type is BeCl2. These outlying these outlying chlorine atoms, the outliers, not the central atom, they have lone pair of electrons that are non-bonding electrons, and they hate each other, and they try to get as far away from each other as possible. And so if you remember your geometry from 9th or 10th grade, if you draw a line segment from the nucleus of this atom to the nucleus of this atom, and a line segment from the nucleus of this atom to the nucleus of this atom, and you think of this as an angle in geometry, you can see that this angle would be 180 degrees. And that's why an AB2 shape is linear. Because if you have a bond angle of 180 degrees, it's a straight line. Now, a lot of this extra credit tomorrow is an absolute joke because I want to show you this. On this sheet, oops, sorry, I actually have to play this. You guys get this purple sheet on the test tomorrow. You get this purple sheet, and the bond angles are on here, but I want to talk about them in how they relate to VSEPR. Look at, if you have an AB2, the bond angle is 180 degrees. They show you on the sheet. I wish I could write on here, but I can't. Oh, all I can do is move it back and forth. And so you can see on here that the bond angle for an AB2 molecule is 180 degrees. You don't even have to memorize it. The ones that are tough are these because the bond angles aren't here. So we're going to have to, you're going to have to memorize these. So I'm going to go shut this off. Okay, so AB2, the bond angle is 180 degrees. Now, all right, exit. Let's go back to this. Now, next, by the way, there's only 5 parent structures, so this is actually a very fast lecture. The next type is AB3. Put this down, AB3. And what happens is if you have A in the middle, valence shell electron pair repulsion theory says that these will align themselves like this. And here's the reason. Sorry, I'm trying to draw good pictures. I'm not a very good drawer. This is B, this is B, this is B. What this notation means is that the B's, there's 3 B's aligned around the A. And picking up the red, again, if you go from nuclei to nuclei to nuclei, knowing that there's 360 degrees in a circle, obviously each of these have to be 120 degrees because 360 divided by 3 is 120. And so for an AB3 molecule, the bond angles are 120 degrees. And again, I'm going to keep going back and forth. It's going to annoy you, but because you weren't in class today, I want to be fair. Notice that the 120 degrees is on there for AB3. Now you can't see me point, but they are on those purple sheets that you get. So don't fret about this. This shape is called trigonal planar. And even though I'm a really bad drawer, let me just go down here and just go again, just a little quicker. You can see, if I do this with BBB, where the trigonal part is coming from. You can see the triangle, and it all sets in the plane. And the other thing I want to tell you is that AB3 has a bond angle of 120 degrees. But in AB2E, because that's the same family, because 2 plus 1 is 3, this shape is bent. I'll show you that in a minute. And that bond angle is, all I want you to know is it's approximately 120 degrees. It's very, very, very close to 120 degrees. But when you erase one of these, which is the same thing as emptying, now you can see why the molecule is bent. But you can see that it's still, because it has an unshared pair there, it still is about 120 degrees. It's a slightly less because unshared pairs are a little bit closer than this electron is a little bit closer to these than this is, and so it squeezes this a little closer, but it's darn close to 120 degrees. So that's what I want you to know, that AB3, the bond angle is 120 degrees, and AB2E1, which is in the same family, the bond angle is approximately 120 degrees. Now, going to AB4, which is crazy, and one of the things, the reason we did this lab is when you do AB4, in 2 dimensions, which is the whole purpose of doing this lab. So carbon tetrachloride, that's AB4. It looks like a big giant plus sign. I mean, in 2 dimensions, this looks like a big giant plus sign. But the reason why we did the lab is it doesn't look in 2 dimensions like it looks in 3 dimensions. What we learned is AB4 is a tetrahedral shape, and it actually looks like, I was explaining this, a tripod with a camera on it or a camcorder. And how we draw this so that it doesn't look like a big giant plus sign is that we have the central atom there, and then we drew the B atom here, and then here's one of the legs of the tripod. And then what they do is, for things that shoot out of the plane in there, they do this little wedgie thing. And if they want to indicate that it shoots in back of the plane, they do this little dot, 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 which means it goes back. But if you see this, you can see that it kind of has a trigonal base if I do that, because a tripod. And then if each of these connects all here, and if I could draw it all, this would supposed to look like a tetrahedron. From your math class, and I think it would be better if the wedge was out here. But AB4 is tetrahedron, tetrahedral. AB3E and AB2E2, these are all the same family. This is AB3E is called trigonal pyramidal, because, and you can flip over on the back and look at this. When you have the A and you take off that top B, sorry, I did something weird. Did you hear it beep at me? Here's the A, and you take off that top B. So we got this B coming here, and then this is wedging out towards us, and then this B is going back. So make it look a little bit more like a triangle. Now there's your triangle, and now you have this pyramid shape. And so that's trigonal pyramidal. But then when you take your when you have AB2E2, what happens is you take off 2. So you just end up with like, actually I'm doing green, this one, and then like maybe this one, because you pulled 2 off. And then that's why you just get an angle. And when I was in grad school, they called these angular, but now they're called bent, which just means you can have 3 atoms in a line, or you can have 3 atoms in an angle, and so they call it bent. But now you can see this on the sheet, and I don't know how to teach this to you, so I just want you to see that the bond angle for tetrahedral, if you look at tetrahedral, it's 109.5, and I don't know how to prove that to you. I was going to ask Mrs. Hires if she knew, but so the bond angle for linear is 180, for trigonoplanar is 120, for tetrahedral is 109.5. And so looking at the back, well, I won't look at the back, but you can see that on the back, people, they don't have the bond angles. So I will summarize them in a minute, but I'm going to go back to here and just do this. An AB4 has a bond angle of 109.5. An AB3E has a bond angle of approximately 109.5. It's actually a couple degrees less. And then an AB2E2 also has a bond angle of approximately 109.5, because when you take off, you know, if kids were here today, I held up the models, but all 4 angles are 109.5, and just because you yank off 2 doesn't mean the other ones stop being 109.5. Okay, this is the hardest one. This is an AB5, because if you remember what an AB5 looked like, is we had A in the middle, and then we had the B on the top and a B on the bottom, and I called those the North and the South Pole. And then we had 3 around the outside, but these were, and again, 1 shoots out, 1 goes back in the plane. And so there's your 1, 2, 3, 4, 5. And this shape is called trigonal bipyramidal. And because you have this trigonal around the equator, and then you have the top pyramid and the bottom pyramid. But the thing about AB5 is it has 2 bond angles. It has 90, but then the equatorial ones are 120. And if I go back to this sheet, you can see, I'm going to go back to this one, you can see that when AB5 is the only shape, it's the 1, 2, 3, 4 shape, because you can't see where I'm pointing, that has 2 bond angles, 90 and 120. Now, the AB5 family is the biggest, because if you look on the back, AB4E1, AB3E2, AB2E3, 3 of these on the back, or more than a third of the back ones, come from AB5. And some weird things go on when you have AB5, because I'm going to go to a new slide. AB4E1 is my favorite shape. It's seesaw. And when you pull off one of those equatorial atoms, you get the fulcrum. It has bond angles still of 90 and 120, like you'd expect. But AB4, sorry, not AB4, AB3E2 is T-shaped. If you look on the back, because here's what happens. Here's A, here's B, here's B, here's B. These other 2 ones we yanked off. If you look really carefully, it's pretty easy to see the letter T. And so what happens is on the AB5, this is why you get extra credit, the bond angles aren't all the same like they are for, and by the way, going up here, this needs to be approximately. These bond angles are 90. Can you see the 90? And 180. Can you see the 180? And so, so we have to say that. And then, let me extend this. When you have an AB2, E3, you pull out this one, and so you get A, and you get B, and you get B, and all the equatorial ones are gone, and now you have 180 again. Because if you look on there, it's linear, just like AB2, so AB2 and AB2E3, where the equator is empty, have the same shape. It's linear. Next one, AB6 is octahedral because they point to the corners of an octahedron. If you're going to draw this in 2 dimensions, I just want like SF6, let's say. I'm not going to do all the dots, okay? I can't even tell you, I do this myself. In 2 dimensions, this looks like a 6-armed snowflake. That is not what it really looks like, but that's how you have to represent it on paper. If you want to represent it more accurately in paper, there's A, and then you have B on the top and B on the bottom, and that is like the x-axis, or sorry, the y-axis. And then you have this coming out, like these coming out towards you, and then these going back in the plane. And so that's how you kind of represent it, although it does look a lot like that, but this wedge means it's coming out towards you. And so this is octahedral. And then if you look on the back, AB5, E1 is called square pyramidal. Why? Because when you pull this bottom one out, you end up with this square base with this vertex of the pyramid on the top. And then AB4E2 is you pull out 2 of these and you end up with just this and this and this and this. And so you end up with a square all in one plane. And so an AB4E2, if you look on your sheet, is square planar. But what's interesting is in octahedral, all of the bonds are 90. On an AB5E1, there's a couple bonds that get squished. They're a little less than 90. But then an AB4E2 is exactly 90 again, and that's because the lone pairs are symmetrically arranged top and bottom, and so they work against each other and they push with the same force, and so it's back to 90 degrees. Now, if I was going to, because you guys weren't here, bring this all together, AB2 has a bond angle of exactly 180 degrees. You can get that off the front. AB3 has a bond angle of 120 degrees. And AB2E1 is in the same family, but we say approximately 180 degrees because the lone pair takes up a little bit more space and it kind of squishes stuff down. But notice they're the same, you just put the approximate symbol. Then you have AB4, which is tetrahedral, and the bond angle is 109.5. And then you have AB3E, which is trigonal pyramidal, and we say approximately 109.5. It's actually a little bit less. And then we have AB2E2, which is in the same family, because all of these are in the same family, and this is approximately 109.5. And then we have AB5, which has a bond angle of 290 and 120. This is between the North and South Pole and the equator, and these are between 2 atoms that are on the equator. So if one atom's on a pole and on the equator, it's 90. If both atoms are on the equator, it's 120. Now AB4E1, which is my favorite, it's seesaw. that still has bonds of approximately 90 and approximately 120. But as soon as you pull out 2 of the 3 equatorial atoms, this thing changes to the letter T. And you have approximately 90 and approximately 180. What happens is these 2 lone pair over here squish these a little bit. So these are a little bit less than 90, and this is a little bit less than 180. So I like, or this is 180, whatever, approximately 180. So notice on the AB2E5, the bond angles don't all match like they do here. And then AB2E3 is linear, and so that is exactly 180. Because the E's are symmetrically arranged around the equator, and so all of the shifts cancel. And then, moving this down, I'm almost done. AB6, you can get this off the front, has a bond angle, everything's 90. And then if you have AB5E1, we say I do this again. It's 90 degrees Celsius. I tend to put C's on degrees because I'm a chemistry teacher. AB5E1 is square pyramidal, and we say approximately 90. And then AB4E2 is square planar, and it's exactly 90 again because of the fact that the lone pair are symmetrically arranged, so they push with the same amount. And that's it. On the back of your test tomorrow, when you draw a molecule, let's say you draw one and it's AB2E1, for extra credit, I'm going to say, what is the bond angle? And so you would say, okay, AB2E1 comes from the parent structure, AB3, and so it's 120, but it's not exactly 120, it's just close to 120. And if you do that on the back, you will get some extra credit. I hope this helps. I will see you tomorrow.